Hi, folks. We're going to take a look at numbers 4 and 5 on page 167. So let's start with number 4. Gives us a table of values that show the speed of a car and then the fuel economy in liters per 100 kilometers. And they ask us to make a scatter plot. So what you're seeing here is a scatter plot. Notice how I changed my scale so that I could see the points more clearly and the type of pattern they show. So they ask us to describe the relation. So certainly we can say it's a non-linear relation. Okay, in fact, it also looks like it's a function. So it's a non-linear function. Then it asks us to draw a curve of best fit, given that it's not linear. So I've got it here printed out. So again, when you're drawing a curve of best fit, you kind of do the best to draw some sort of curve that passes through most of the points. Sometimes it won't even pass through all the points because it's about drawing the curve that looks closest to the pattern that's formed. So let's say here, that's good. And see, turn your paper around to get something that looks like it passes through or represents most of the points. Okay, now I'm going to continue it because they're asking us to do an extrapolation. Okay, so there's our curve of best fit, and when they ask for an extrapolation, they don't use the term, but this is what we call it, is when we're trying to use this curve of best fit to estimate a value for something outside of the range that we were given. So the range of values we were given were between 10 and 150, and in part D, they're asking us to determine an approximation for 200 kilometers an hour. So it looks as though at 200 kilometers an hour, we're at about 40 liters per 100 kilometers. Okay, so that's significantly larger than the other values, but based on the way this curve starts to grow more quickly, maybe it shouldn't be too surprising that we get a number so high. All right, so let's take a look at the last question. It says the car does not get very good fuel economy. How would a graph of the car with better fuel economy look, and why? Okay, and this question here is actually going to lead us to where we're eventually going in this first quadratic functions unit. All right, so first of all, I think we can say that if it's going to have better fuel economy, at the very least, all the points on the curve should be lower. Okay, meaning less liters per 100 kilometers based on the values. Okay, now by the way, it's pretty reasonable that at around 60, 70 kilometers an hour is where you get the best fuel economy. So that's usually how it works, whereas if you're driving very slow, not so great, and the faster you go, it gets worse and worse. But I would say that a car that has good fuel economy not only would have lower values, but wouldn't start increasing so quickly as the speed got higher and higher and higher. So I would say not only would the values be lower, but I would say that this curve should be increasing. We can say it's wider. Okay, it doesn't increase so quickly. So as you get to higher speeds, it doesn't increase quite so quickly. All right, so what we can say is that the points should be lower on the graph, and this curve, okay, should be wider in its shape so that it doesn't increase quite so quickly as time goes on. All right, so what we're seeing here is a curve that would be similar in terms of the shape, but has some differences, would be lower on the graph and would be wider. And like I said, this is the type of thing we're going to be studying in this unit. So let's take a look at number 5, and I think we're going to see something a little similar. So let's go back to our graph. So I have my, I'm going to take out these values here, and I put in a second table for number 5, and you see that I don't see much. All right, so remember that when you're using Desmos, go use the wrench here to change the values that you're interested in. So I look at the x-axis, I'm only going from 1 to 7. So I'm going to change this from, say, -1, and I'm going to go up to, 10, not more than that. Okay, and then for the y's, I see the y's are going from 25 to 270. So I guess I'm going to change this to about 300. And now we see something a little better. So I'm going to zoom in a bit. Okay, and now we start to see that again, it's not linear, but they seem to be decreasing over time. Okay, so by the way, what do these points represent? They represent the rebound height for a ball that's bouncing. All right, so here's our scatter plot. Again, describe the relation. It's nonlinear, and it seems to be decreasing over time. Okay, so to draw a curve of best fit, again, we'll go to do that manually here. So again, sort of flip your paper around and try as best as possible to draw a curve that's close to most of the points. So don't worry if it doesn't actually go through every single point, but there you go. That's a pretty reasonable curve of best fit, passes through a lot of them and is close to all of them. All right. So if we take a look here at what they're asking us for, they're saying, how would the relationship change for a ball that was bouncier? Okay, so let's see what would happen. Now, this starting height, presumably, seems to be about 400 centimeters. The starting height shouldn't be different because you're still dropping the ball from the same spot. But what would change is that if it was bouncier, it would bounce higher every time. Okay, so again, I would expect these values to be all bigger than they are. So I would still expect it to be a curve because we know there will be some loss of energy as the ball bounces, but you would expect it to lose less energy so that it would bounce higher each time. So what would happen is, again, it looks like this curve is going to become a little wider. It's not going to decrease in this case here quite so quickly as the original one. All right. Now, another thing I want you to think about is this is the relationship that just shows the rebound height. What if it actually showed the height of the ball, not per number of bounces, but the height of the ball with respect to time? You got to think that you'd have something that would be going down. Okay. It would hit the ground and then go back up. Okay. And then it would go back down and then go back up. Go back down, go back up. So you'd have something that looks like this. So here we start to see that we're going to need different types of functions to describe different types of scenarios. Okay, this curve we drew here works perfectly well if all we care about is the rebound height every time it bounces. Okay, but we're going to need a different type of function if we want the height of the ball with respect to time, because the height is going to be going up and down and up and down, again going less high each time, but it's going to create a more complex function. So these are the things that you'll be studying over the next few years. This year, though, we're going to be focusing in on curves like that look like the ones we've drawn so far, okay? And we'll define them later on. Okay, that's it for this one.